Okay, for introduction, automated curtain operation. Utilize an Arduino microcontroller and a light dispensation resistor (LDR) sensor to automatically open or close curtains based on light intensity or schedule times. For second point is energy efficiency. Help regulate natural light, reducing any need for artificial lighting and enhancing room insulation, contributing to energy savings. For number 3, convenient control. Ideal for large windows and smart home, enabling hands-free curtain control for added comfort and ease. For the last point is customizable features. Support user-defined settings such as light sensitivity adjustment, time-based scheduling, and different schedule for weekdays and weekends.
It compares two boost converter design, the smart boost converter and the DC-DC boost converter using a 555 timer IC. The smart boost converter features 11 components including Arduino Uno and LDR, designed for steady-state operation in applications like LED drivers and solar power. Meanwhile, the 555 timer IC base design focus on compactness, making it suitable for renewable energy and portable electronics. Both are boost converter, but vary in size, efficiency, and application.
Then for design specification, this figure has shown 555 timer, U1, capacitor C1, C2, C3, and C4, then the resistor R1, R2, and R3, a variable resistor RV2, an igniter L1, a diode D1, NPN and PNP transistor Q1 and Q2, and a MOSFET Q3 have formed the parts of the boost converter. An input DC voltage of 12 volts V1 is increased by the converter to the higher output voltage of exactly 24 volts. RV2 resistance can be changed to alter the output voltage. The motor of an Arduino control automatic curtain system, which needs 12 volts to operate, is meant to be powered by this boost converter.
For the design calculation of our project, which is DC-DC boost converter, as you can see, the formula V output is equal to V input per 1 minus duty cycle. So our project, we set voltage input is 12 volt and voltage output is 24 volt. By using this formula, we can find out our duty cycle is 0.5. For next is determine minimum inductance. The minimum inductance ensures the converter operate in continuous conduction mode and avoid excessive current repair. Determine the minimum inductance that needs to be used for this circuit is calculated by this formula. Minimum inductance is equal to bracket 1 minus duty cycle square multiply the load resistance per 2F. F is switching frequency. So we have 10 ohm load resistance and we can get our minimum inductance is the 25 mu Henry.
At DC-DC boost converter, this is a calculation for average inductor current. I add is current inductor, Vs is supply voltage, D for duty cycle, and R for load resistance. So this is our formula. This is formula that given we use to find IL, average inductor current. We get 4.8 amperes using this formula. For DC-DC boost converter, this is formula to calculate the capacitance. The formula that given is C for capacitance, D for duty cycle, R for load resistance, and R for ripple factors. So from the formula that given, we can find capacitance value. The value of capacitance is 500 nanofarad.
Our chosen topology is a boost converter that steps up a 6 volt input to 24 volt output ideal for powering a 12-volt motor in an automatic curtain system. Key components like the inductor, capacitor, diode and MOSFET ensure reliable energy transfer operating in different conduction modes. This topology is efficient, compact, versatile and easy to integrate, making it a perfect fit for our application.
So, for our project, we use DC-DC boost converter. Firstly, the purpose and function. DC-DC converter regulate the output voltage by managing energy transfer, even when the input voltage fluctuates due to factors like temperature or radiation. This is achieved by controlling energy injection and absorption during its switching cycle. Second operating mode, the converter operates in continuous conduction mode (CCM) or discontinuous conduction mode (DCM), depending on its energy, storage capacity, and the length of the switching period. Third, boost converter circuit. The basic component includes an inductor, switch, diode, output capacitor, and load resistor, ensuring efficient voltage step-up and regulation.
So in simulation part, we simulate our project by using the PSPICE application. So the simulated circuit is a boost converter that uses a 555 timer based pulse width modulation, which is PWM signal generator, to control the switching of a MOSFET. The circuit functions as a boost converter controlled by pulse width modulation, with the 555 timer producing a PWM signal based on the RC network made up of R1, R4, and C1. A potentiometer controls the duty cycle of this signal, which sets the on and off periods of the MOSFET. The output voltage is directly affected by the change to the duty cycle. The inductor in the boost converter stores energy from the 12-volt input supply while the MOSFET is turned on. The inductor releases energy when the MOSFET turns off, and this energy adds to the input voltage to raise the output voltage. The output is stabilized by the diode and capacitor, guaranteeing that the load receives a steady DC voltage. So the output voltage can be properly adjusted due to the function of potentiometer. With a higher duty cycle results in a higher voltage. So for the simulation output waveform graph, this figure has shown the waveform for the voltage, current, and power dissipation of the input and the output of the design circuit. The output voltage can be properly adjusted due to the function of the potentiometer. With a higher duty cycle results in a higher voltage. The simulation have shown that a 12-volt input voltage can result a boost output of about 24 volt for this circuit. The timing components, which is R1, R4, and C1, can determine the PWM frequency, which runs at 50 kHz with a 40 microsecond interval.
Now, the hardware construction. As you can see in the picture, we use different variable of resistor, capacitor, and transistor. We also use inductor, variable resistor, and 555 IC timer. We use breadboard for our hardware construction due to it is easier for us to troubleshoot and make some adjustment. We also use jumper wire and 12-volt battery.
Now move on to the calculation of the power losses and efficiency. First, we calculate the average inductance current is equal to duty cycle multiply voltage input multiply bracket 1 minus duty cycle per bracket switching frequency multiply minimum inductance. After substitute the value inside this formula, we can get the result is 2.4 ampere. Next is calculate the power conduction losses. So we using the formula is power conduction equal to average inductance current multiply the voltage input. So we get the 28.8 watt. Next, we calculate the switching inductance current and switching off voltage to find out the power switching. For the switching inductance current is equal to voltage output square per bracket load resistance multiply voltage input. So we can get the current switching inductance current is equal to 4.8 ampere. For switching off voltage is equal to voltage output plus voltage diode. So is 24 plus 0.7. The final result is 24.7 volt for the switching off voltage. After that, we can find out the power switching. The power switching is equal to 0.5 times switching inductance current times switching off voltage times frequency switching. So we can get the power switching is equal to 2.964 megawatt. And the power diode for our project is 0.3535 watt. So to find out the total power losses, we total up the power conduction losses, power switching, and power diode, and we get the 2.964 megawatt. So last for the efficiency is equal to voltage output times duty cycle per voltage input. So we get the final result is 1 for the efficiency.
For discussion for this project, in residential use, enhance the convenience, privacy, and energy efficiency by automating curtain operation based on the light levels or schedules, reducing reliance on artificial lighting. In commercial and specialized application, ideal for office, hotels, retail spaces, greenhouse, and public areas, optimizing natural light use, energy management, and comfort. And and in educational and learning tool, serves as a par- practical platform for teaching automation, power electronics, and programming, allowing students to explore and expand its functionality. Conclusion in point, core functionality combines the Arduino microcontroller, LDR sensors, and motor to automate curtain operation based on light levels or schedules, with a boost converter ensuring stable power supply and efficient functionality. Key benefits enhance the convenience, energy efficiency, privacy, and thermal comfort while reducing reliance on artificial lighting and improving daily living quality in residential and commercial settings. Versatile and application in homes, office, hotel, greenhouse, and educational spaces, offering customization for energy management, improvement, and practical learning in program and automation. In future enhancement, potential upgrades include addressing voltage ripple use in advanced filtering, integrating IoT features for remote control, and improving scalability for seamless integration into a smart home ecosystem. And for the references, we using website in IEEE and many other websites to find our references. We using Google, also using Google Scholar to find our source, and using Sci-Hub to find its journal or whatever that we can find as a sources. And then we will cite we using a my citing machine to cite every sources or references that we can use that have similarities in our project. So thank you.